We'll go from current slide. And before we start on the calculus part, let me go over this one fairly major announcement. You probably have received the emails, which I'm sure y'all are all checking diligently, okay? I got this one, it was after this class started on Monday, so I didn't see it until Tuesday. And when I first saw it, I thought, how did I get into this part of my email? The subject line was Lawson State Fall 2018 surveys have opened. I thought, how did I get back into last fall? Okay. But I went on and opened it anyway, and the content says, students have been notified that their summer 2019 term surveys are available. What they did, they just used an old email and forgot to change the subject line. They changed the content but not the subject. So you should have gotten something corresponding to this and with the correction made in the subject line. So have any of you seen that yet? Good. Okay, any of you done them yet? Okay, you don't have to have them done yet. They have to be done by the 8th of August. Now the 8th of August is well after the term is over. And back when I was an undergraduate, that long after the term was over, if I hadn't done it by then, it wasn't going to get done. So, hey, don't put it off. And then say, term's over, etch a sketch, shake the thing, and everything's clean, white, slick. Don't do it. Do it sometime. If you think you might forget, don't get it done now. If you really want to wait and see what your final grade is and that kind of stuff, you can wait till then, but be sure you do it before August the 8th. Okay? On the announcement, there are two really important things there. One is a link. Click on the link, you go straight to the surveys. So you don't have to go through the website and all that kind of stuff. Go to the link, go straight to it. Okay? Secondly, tells you how to log in. And most of you are not Lawson students, right? You're all transients, pretty much. Okay? So use your 7-digit Lawson ID number. Okay, you know it's 120 or something like that with 4 more digits. Okay, use that as your login, and then your birth date is your password. Now the birth date's an 8-digit number. The first 4 digits are your year of your birth, and this won't be true for you, but for me it would be 1951. No, you'll be quite that old, maybe. Okay, and then the next 2 are the month of your birth. 01 for me. Be sure you put a 0 if it's a single-digit month. And then the date of your birth is the last 2 digits. For me, 07. Be sure to put a 0 in front if it's a 2-digit number. Okay? Please get those done before August the 8th. Sooner the better, but before August the 8th. All right. Any questions? All that's in the email. Go to your emails. Check it out. Use the link. Go to it. And Bill, you've done them before, right? How long did it take?
Except the log session, 3 or 4 minutes.
Is what?
3 or 4 minutes.
3 or 4 minutes just to do the main part of the survey. And I could recognize, most of the time it's completely anonymous what you put down, but when he put remarks, I knew exactly which remarks came from Bill because he didn't like the book. He liked the Thomas book, you know, and I could tell that was Bill, but the rest of them I have no idea who put what. You know, I could tell the comments only. Couldn't tell the numbers. No one will ever know what you did, what you marked for anyone. So don't worry about being discovered. You won't be. Be honest about it. Knock it to it. Okay? All right. Any questions then? Calculus or otherwise? All right. We're in Chapter 9, and the title of Chapter 9 was Infinite Series, and 9.1, though, was not infinite series. It was sequences. 9.2, however, is going to be series, and then more on convergence. We did a little bit of convergence with sequences. We're going to talk more about convergence with series. Excuse me, I've got hiccups. All right, our objectives here are to understand the definition of a convergent infinite series, And we'll use properties of infinite geometric series, a very special kind, and we'll use the nth term test for divergence of an infinite series. And too bad we won't get to do too much in Chapter 9 because the subsequent sections after 9.3, interval test and the P-series, comparison of series, alternating series, ratio and root test, all these are good stuff. Then into Taylor polynomials and approximations, really, really, really powerful stuff. It's just not time enough to do all this and get Chapter 10 done and get what we're going to do in Chapter 11. So I'm going to have to curtail it, just talk about sequences in series. And if you'll notice the course description that was in your syllabus, it said sequences in series, okay? I'm abbreviating that and doing it straight by the letter. We just don't have time to do all those great ones. If you need them, you've got the text or some text, you can follow up. Hopefully what you'll get is enough information to work with the others if you need them. Okay, so let's start with infinite series. Anyone want to hazard a guess of what's the difference in a sequence and a series? A sequence is a list, usually of numbers, okay? Usually with some sort of pattern, but it's just a listing of the numbers. What a series is a sum of a sequence, okay? It's the sum of some sequence. One important application of infinite sequences is representing infinite summations. Informally, if a sub n, now this is the symbol for a sequence, if a sub n in the curlicues here, often called braces, a sub n is an infinite series, then the summation from n equal 1 to infinity of a sub n, which would be a sub 1 plus a sub 2 plus a sub 3 plus a sub n, and it keeps on going until it keeps on going, okay? It's an infinite series. That's called an infinite series or simply just a series. So a sequence is a listing of numbers, usually with some pattern to them, and a series is a summation of such a sequence, okay? Now, the numbers, a sub 1, a sub 2, a sub 3, are also called the terms of the series, okay? Because remember, way back in algebra, you called anything separated by a plus or minus sign a term. So these are your terms, just the same definition as before. They were the elements of a sequence, okay, but they're the terms of a series, okay? For some series, it is convenient to begin the index at n equals 0, not n equal 1. Or you can use any other beginning number if you wanted to. There's nothing special about 1. It's just where most of them usually begin. Okay? As a typesetting convention, it is common to represent the infinite series as this, without putting the n equal 1 to infinity. You usually just assume it's beginning at 1 and going to infinity. If you're using some other starting point, then you do it. But the n is the counter, okay? 1, 2, 3, 4, 5. Okay. Now, I just finished Cal 1, and they were just getting into it and they usually use your I as the counter and the n as the last term, the maximum. So if you're used to that, this is using n as the counter and usually using infinity as there is no last term because we're dealing with infinite series. Okay, in such cases, as we were just talking about, the starting value of the index must be taken from the context of the statement. So to find the sum of an infinite series, consider the following, okay? So we started with a sequence, add them together and you get a sum. Well, we're going to take the partial sums, not the infinite, but where they start, and that's going to make a new sequence, okay? Because these are going to be the sequence of the partial sums. So if you just count the first value, that's called S sub 1, sum of just 1. S sub 2 would be the first 2. S sub 3 would be the first 3. S sub 4 the first 4. S sub 5 the first 5. S sub n the first n of those sums. Now, those are finite sums. They stop. They have an end. Now, and if you look at the sequence of these sums, 1, 2, 3, again, this is just a collection of numbers. If the sequence of partial sum converges, just like we talked about in the last section, then the series is said to converge and has as its sum indicated in the next definition. So we're going to get to the definition in just a second. So we started with a sequence, add them together, you get a sum, then you just look at it. And you get a series, take pieces of that series, regular pieces, 1, 2, 3, 4, yeah, and have the partial sums. That makes a two sequence. So we're back to sequences again, and here's where we go from there. Here's the definition for a convergent and divergent series. For the infinite series, summation of n equal 1 to infinity, or just that, okay, a sub n, the nth partial sum is S sub n is, just like we saw on the last slide, a sub 1 plus a sub 2 plus a sub n all the way up to a sub n, but stop there. It's a partial sum, okay, stopping at a sub n. If the sequence of partial sums, now the sequence of these partial sums, S sub n, that's the sequence now, converges to some number s, then the entire infinite series, this thing right here, also converges. The limit of this s, if this sequence of partial sum converges to s, the limit s is called the sum of the series, and that's what it's said to be. S is the sum of that infinite series, which is the limit of your partial sums, the sequence of your partial sums. If S of n, this sequence of your partial sum, diverges, then the whole series diverges. So in other words, if this thing doesn't narrow down and come to some limit, then the series diverges. Okay. So let's look at one. Here is a series, summation of n equal 1 to infinity of 1 over 2 to the n, and this is going to be 1/2 when n is equal to 1, 1 over 4 when it's equal to 2, 1 over 8 when it's 3, 1 over 16 when it's 4, and so on and so on and so on. Okay? Now, here is the first of your partial sums, 1/2. What would be the next partial sum? Let me get my pen set up. Okay, what would be s sub 2? 1/2 plus 1/4, which would be, can't we do it? 3/4, perfect. What's s sub 3? 1/2 plus, 1/4 plus 1/8, which would be 3/4 is 6/8 plus 1/8 would be 7/8. S of 4 would be that plus 1/16. This would be 14/16 plus 1/16 would be 15/16. S of 5 would be, that's 30 seconds, plus one more would be 30 seconds. I can't write, okay. And anyone want to make a guess about S6? 63/64. And S sub 7 would be denominator 128, because that's doubling every time, and that would be 127 1/28. Anyone see a pattern here? Does that sequence of partial sums seem to have a limit? What? So, yeah, it's getting closer and closer to 1. Exactly. In fact, you can probably do a general form for that, it would be 2 to the n under 2 to the n minus 1. 2 to the n minus 1, because that's what it's coming out every time. 1 over 2, 3 over 4, 5, 8 over 7 over 8, yeah. So the denominator is always 2 to the n, and the numerator, oh, that's not quite right, is it? 3, 4, yeah, 5, 6, yeah. Yeah, 2 to the n, and the numerator is 1 less than 2 to the n. Okay? And that certainly is going to converge to 1, because that would be 2 to the n over 2 to the n minus 1 over 2 to the n. That goes to 1, and this is going rapidly to 0, okay? So 1 minus 0 is 0. Make sense? Okay? All right. Let me erase my scratch and see what they're going to do. S of 2 is 1/2 plus 1/4. They're just listing. Oh, it's equal to 3/4, just like we did. S of 3 is that, which is 7/8. S of 4 is that. Oh, S of n. They skip right on to S of n, which is 2 to the nth minus 1 over 2 to the nth, which is exactly the pattern you see emerging there. Okay? And that, hopefully you see, obviously has a limit of 1. Okay? Now, it follows that the series converges and its sum is 1. Now, I don't know if you've heard of this, you might call it a puzzle or riddle or something like that, but if I were going from here to the wall there, okay, and I wanted to get there, and every step that I took, if I could take it that long, was going to be half the distance to the wall, right? So the first step would get me right about here, and then the next step would get me right about here, and the next step right about here. Would I ever reach the wall? No, okay? I'd be awfully close, but you never quite get there because you're only going half. That's exactly what this sequence is doing. It's going half the distance left to go, more, but not ever quite getting there. So ultimately the sum is the wall, 1. Okay, you make 1, but that's the limit. You never actually get there because it's an infinite series. Infinite series, infinite sequence as well. Okay. So, I think that's all of example 1. Oh, no. Oh, wait. There's the B part. I hadn't turned the page yet. Sorry. All right. Here's the B part. And they get started already. The nth partial sum of this series, which is series, the summation of n equal 1 to infinity of 1 over n minus 1 over n plus 1. So the first one would be, when n is equal to 1, that would be what? Second? 1 minus 1/2. Good. The next one would be 1/2 minus 1/3. The next one, 1/3 minus 1/4, and so on and so on and so on. Infinite series that keeps on going. Now, any of you want to hazard a guess what if that one has a limit? Okay, what would it be? Okay. Let me tell you an easy way to look at it. Notice here, minus 1/2 plus 1/2. Minus 1/3 plus 1/3. Minus 1/4 plus 1/3. 1. That's also going to 1. Looks a lot more complicated, but that's also going to 1. Okay? And why? Because all those middle terms disappear. You just left with the first one and the last one would be 1 over that last n plus 1. Okay, that's the nth partial sum. And of course, okay. The nth partial sum then would be this one. And if you did the math here, as n is going to infinity, this is certainly going to 0. So that limit is also 1. Okay. Because the limit of S sub n is 1, the series converges and its sum is 1. The sum of the infinite series is 1. The partial sum, even the nth partial sum, is approaching 1, but never actually gets there. All right, here's another. Oh, how about that? That's pretty easy, isn't it? It's an infinite series of n equal 1 to infinity of 1. What would that be? 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. Okay, does that have a limit? No. Okay, that's getting bigger. Every one you add, never. It diverges because the S sub n, the sum of this is, if you have n of those 1s, 1, 2, 3, 4, 5, n of them, n times 1 is n, and that is n going to infinity, that's exploding, going to infinity. The sequence of partial sums diverges, so that infinite sum, that series, diverges. Big. Okay? Without a doubt, diverges. All right, is there a D? No. Now, that one we talked about before was called a telescoping series because these two inner terms always cancel each other out. Okay? Now, if these were numbers that were getting bigger, yeah, you're wiping all these out, but the last one is infinity, and the first plus the last, then it would. So just because it's telescoping doesn't mean it has a limit. Okay? If the second term is the second term of each one of these is smaller, which in this case it is, then it will have a limit. Okay. All right. They didn't go into that much detail, but there it is. Because the nth partial sum in that series is b sub 1 minus b, well, actually, I said that wrong. What do y'all know? Minus b to the n minus 1, because there's a minus there. It follows that the telescopic series will converge if and only if b sub n approaches a finite sum as n approaches infinity. Moreover, the series converges, then its sum is going to be at b sub 1, because that last one is going to have to be going to 0. Okay? Wait, is that right? No, if and only if the b sub n approaches a finite number. So that can approach a finite number, then the difference, the sum, infinite sum, will be b1 minus whatever that finite number is. It may not be, that may not be going to 0 if it's going to a finite number, then your answer will be b1 minus that finite number. I don't know if they give an example of that. I don't think they do. Okay. All right. Yes, they might. Example 2 is not given in the text and the slide set, so let's go back. Goodness gracious. All right, that might be the most white space we have right here. Example 2. Find the sum of the series, the summation of n equal 1 to infinity of 2 over 4n squared minus 1. Okay. Now, they do this in a fairly strange way, but it's true. let's do it. Now, I hate to say it quite this way because we probably aren't supposed to think of it quite this way, but what is a summation awfully close to being? Where do we translate from sums to second? Infinite, right? And what do we do if we had an integrand that looked something like this? How do we evaluate it? Can't do it by substitution. Second? I can't hear. Trig? Perhaps. That was a hard way of doing it. And you're a hard worker, I can tell. And I'm sure that will work somehow, but there's an easier way.
Two times the element of 1 over 4 to the n 4x minus 1 dx.
Okay. Means?
Bring out the 2.
Huh?
Bring out the 2. 2 times
Yeah,
the
yeah.
integral.
Right. Okay, yeah. 1 over that. Okay.
Yeah. Dx.
And then how would you do that? That interval. Then you do trig substitution? Or something else? Huh?
Can't think now.
Okay. Trig substitution, again, another hard worker here. But there is an easier way. Second?
You want to factor that or something?
Yes, that sounds like a good idea. Let's factor that denominator, and what do you get? 2n plus 1 times 2n minus 1. Now, whether you factored out the 2 or not, which I like the idea of factoring it out, that would be 2 times the summation of n equal 1 to infinity of 1 over 2n plus 1 times 2n minus 1. Now, how would we do that if that was our integrand? Or how would we did this in this course, didn't we? Chapter, I can't remember the chapter number. Techniques of integration. Say again? How? Okay, and what do we call those? Anyone remember? Partial fractions, yes. So let's see what happens if we do that. If we set this up and say, what is 1 over 2n plus 1 times 2n minus 1 if we broke this down to be an a over 2n plus 1, well, I don't need parentheses there, plus b over 2n minus 1. How would we, what would be our first step to approximate that? Oh, that was one test ago. Who cares about that anymore, huh? We're through with that. Yeah, that's what we want to do, find A and B. What was our technique? Multiply everything by that common denominator. 2n plus 1 times 2n minus 1. Multiply this by 2n plus 1 times 2n minus 1. If I had been planning ahead, I would have given myself more room. 2n plus 1 times 2n minus 1. Okay, here the whole denominator disappears, which is what we wanted. Here, this denominator disappears, but leaves us something. What you're left with on the left is 1 is equal to a times 2n minus 1 plus, and here the 2n minus 1 goes away, and you're left with a b times 2n plus 1. Okay? Now, what was our next little trick? Second?
Use this set to 0.
Okay.
Use this set of one of the values so that equal to 0.
And how do you do that?
So you can make
exactly right on the technique. How do you do it? Say it. You said it? Yes, n equal 1/2. That'll wipe out this one. So this will be a 1 is equal to an n equal 1/2. This will be 1/2. 2 times 1/2 is 1, minus 1 is 0, so that goes away. So then you have 1 is equal to b times, and 2 times 1/2 is 1 plus 1 is 2. So b is equal to 1/2. Okay. And hold this here, right?
Yes, sir.
Okay. Okay. I'm going to wait to repeat the announcement until more people show up, so I'm going to wait till around halftime when we take a little break. Okay? So I got b is equal to 1/2. What would be the next trick you would use? Yeah, how do you do that? Yeah, this was n equal 1/2, and what do you say to use? N equal negative 1/2. And on the left-hand side, you'd have a 1 is equal to, and on the right-hand side, if n is negative 1/2, that gives you a 2 times negative 1/2 is negative 1 minus 1 is minus 2a, and on the right, on the far right term, that goes to 0. So that means that a is equal to positive 1/2. All right? So then let's change. Same thing will work here. This is 2 times the summation from n equal 1 to infinity of, I'm going to put the positive in front, 1/2 of, where did I have my b? Over 1 over 2n plus 1 minus 1/2 times 1 over 2n minus 1. And notice the 2 here and the 1/2s wipe out, okay? You can factor out a 1/2, get it with the 2, and they go to 1, okay? So you're left with just that one, okay? Now, let's just list a few of those terms. That would be 1 over, when n equal 1, that would be when n equal 1. What's that first term? 1/3 minus second 1, just 1. Okay, 1 over 1. I guess I'll leave that. Okay. I erased too much. Oh. Okay. Because n equal 1, that would be, yeah. Okay. Plus, the next term would be when n equal 2, 1/5 minus 1/3 plus 1/7 minus 1/5 plus 1/9 minus 1/7 plus, I'm going to quit in a minute, 1 over 11 minus 1 over 9 plus dot dot dot. And what happens here, not quite looking the same as before, but all these disappear. And ultimately, the last one is going to, as n goes to infinity, that's going to be a very large number. So what we have is, oh, and I forgot these two disappear. And what do we have? Negative 1. Okay? That one does seem to converge, and it converges. How did I mess it up? They have it as 1. Did I get my... Yeah. Oh, I did do it backwards, didn't I? This was over 2n minus 1. I did it, sorry. The minus goes first and the plus goes second. I was trying my best to get them right, and I crossed them up. So this would be, forget that. It starts with the 1 minus 1/3 plus 1/3. Okay. Sorry. I don't know how I did that. Okay. Plus 1/3 minus 1/5 plus 1/5 minus 1/7. You get the idea, and it just keeps on going. So these cross out, so you're left with 1. Sorry. I went to all the trouble to do that and then put it over the wrong one. I actually did it right up here, okay? Or maybe I just changed it. I don't know, but anyway, that should have been the first one, okay? So it's a +1, not a -1. Okay, so that was an example of a telescoping form. But you don't get it until you do the, and I don't know if a trig substitution will give you a telescoping form or not. This one would, okay. Trig substitution might work, but I don't want to go there. Okay. So let's now move to a very special kind of series, and this is the geometric series. All right. This geometric series, we just had one earlier, okay? That one that we did before, 1/2 to the n. That is a geometric series. In general, that kind of a series, and here's another way to express it, the summation of n equals 0 to infinity. It doesn't really matter you're starting with the 0, but they are, okay? A times some ratio r raised to the nth power. Here, our a was 1, I think. The ratio here was 1/2, okay? Because your first term was, now this was starting with n equal 1, but that would still be 1 times 1/2 to the first power plus 1/2 to the second, 1 times 1/2 to the second power plus, yeah, you're just doing this, you're raising, every term has is a ratio of the previous term, common ratio to the previous term. This is 1/2 of that, this is 1/2 of that, this is 1/2 of that. So you see, it's a common factor between each term. Here it happens to be 1/2. Now this is a geometric ratio as long as the r is not 0, okay? That doesn't make a very good ratio, does it? Okay? Because that would be 0. And that would obviously be 0. Okay, you wouldn't have anything there. Okay? So, we don't have r equals 0. The convergence of a geometric series with a ratio r, diverges when the absolute value of that r is greater than or even equal to 1. If the r, absolute value of that r is less than 1, then the series converges, and here's what it converges to. They give you the answer right here. Amazingly. No matter what a or r that you have, as long as the r absolute value is less than 1, and infinite series is going to be a divided by 1 minus r. So if that r is even close to 1, like 1.9, okay, I mean 0.9, as long as it's less than 1, it's going to take it's going to be a big number here, because 1 minus 1.9 would be 0.9 would be 0.1. So if your a was anything, multiply it by 10, that's your answer. Okay? That's what it converges to. So if the a was 4 million, pretty big number, you might not think that would converge. And if that r is close to 1, it'll still converge. That would be 4 million divided by 0.1, which would be 40 million. Okay? But it will have a convergence. Big number, but it will converge. As long as the absolute value of r is less than 1. If it's equal to 1, nope, won't converge. Of course, anything greater than 1 will not converge. Okay? Geometric series. Really powerful, useful, and simple formula. Okay? Nice to have. Okay. And the proof for this one is really a pretty clever proof. I remember when I was in school, as in, may have been early high school, but it may have even been later junior high. We learned how, I believe it was junior high at least, to get the decimal equivalent of any, no, the fractional equivalent of any repeating decimal number. Did y'all ever do that? Don't remember. You multiplied by the power of 10 that represented the number of digits in the repeating part. Like if it was 0.73745454545, multiply by whatever digits to get you to the first repeating part, and then by 100, because that was a 2 thing, and then subtract one from the other, and this will be a ratio of 9 something, and that all the repeating part disappears, and you have a ratio, and then you do it. It's the same type thing here. I probably shouldn't take the time to do it because they show it in the book, but you, if your S, they call S sub n, is equal to AR plus AR squared plus AR cubed plus AR to the 4th plus ... Okay? Multiply this by R. R times S sub R, S sub n, I can't read my own writing here. Okay, and this goes up to AR to the nth. Okay, keeps on going. Okay, then this would be A sub R. When you multiply R times this, you get A sub R squared plus A sub R cubed plus A sub R to the 4th plus ... A sub R to the nth, and you'd have one more A sub R to the n minus 1. N plus 1. Yeah, that is a plus there. Okay. Sorry, I'm at the end of the page. Okay. Now, if you subtract the top from the bottom, I believe is how we do it, the S sub R's go away, and you're left with one, well, you get S sub n times 1 minus R. No, the bottom from the top. Subtract the bottom from the top. And here, on the right-hand side, you get A sub R, and then all these subtract off, okay? And then divide by 1 minus R. S sub n is equal to A times R divided by 1 minus R. Wait a minute, I've got an extra R in there. Oh, I'm sorry. The first term is just A, and then A, yeah. And this would be A sub A R. So these go up. So that's just A on top. Sorry. My eraser isn't erasing. Okay, there we go. So that's how you get the sum to be that. It's pretty clever proof. Let me see. Oh, whoops. Okay. Yeah. Okay. So that's how we get that same technique up there. Now, here's example 3, and this is on the next page. And by the way, over on page 601, in the left margin, for those who have, well, let's see, I skipped another one. Let me show you some other example. Remember that first one, the infinite series, 1 over 2 to the n. The first is 1/2, and then add to that 1/4, so that's 1/2 plus 1/4 is 3/4. Add to that 1/8 and 1/16. Everything that's left, when you have this, take half of it. Take half of that. Take half of that. Take half of that. Half of that. Half of that. So that's what you're doing, and sure enough, you're coming to 1, but you never quite get there because there's always another little piece in the middle here. This is another proof without words. This is, and by the way, both of these have articles attached to them, so if you wanted to take a look at those, you could, if you wanted to use that as one of your bases for your research paper, which I guess I ought to, while I'm thinking of that, let me go on and get this set. Over just in the last day or two, I've received my first paper from this, my best class ever, of course, and I've received one research paper, okay? Now, I understand some reasons for some of you because y'all told me before, but look, we're running out of term, folks. What is it? Less than 3 weeks left, or right at 3 weeks left? That's all, folks. Okay, that means just 2 or 3 weekends left. Don't let them pass by without getting your papers done. Now, while I'm on that subject, the first test, I think I received, I probably have gotten most of those in. I've just received one recent, well, take that back. One, the staple caught on the previous paper, and I'm misgrading it. So I have a grade that I did have in, but I have two people haven't turned in the first test. One of them hasn't been here in a while. The other has, so I'll just leave it like that. So please get the first test in. And the second test y'all have had for a little bit now, so be working on that as well. Okay, so not too long, we've had a little bit. Okay, have that paid political announcement before we move any further. Okay, here's an explanation, proof without words, and I'm not going to go into detail here, but it looks like a pretty interesting little approach here, and it's basically giving your geometric sequence another proof of it, but this one not even using any words and really just using geometry. So, and maybe that's why they call it a geometric series, okay? Because you can do it just using that. All right, that said, let me turn on to page 3. Example 3. Is this a geometric series? What do you think? Similar enough to what we were doing. What's different about it? Number one, if there were parentheses here, 3/2 to the end, that might be a geometric series, it's not going to converge. Okay, but this isn't. It's only the 2 raised to the nth power. So what is your A and what is your R? Those are the 2 things you need to know. Basically, show you in that next step. A is the 3 and the R is the 1/2. That's the common ratio between each of these things. So you're multiplying each term by 1/2. So if that's the case, that looks like a geometric ratio. What is the ratio? Just 1/2. Is that going to converge or diverge? Converge because the ratio is less than 1. Okay, the absolute value of the ratio is less than 1. And what will it converge to? A over, second, 1 minus R. And your A was 3, and your R was, so 1 minus 1/2 is 1/2, so that converges to second 6. Perfect. Okay? That wasn't too bad, was it? Okay? Especially since they did the first step for you there. Okay? That has a ratio of 1/2 with A equal 3. And because that ratio is less than 1, absolute value is less than 1, series does converge to A over 1 minus R, which in this case was 3 over 1 minus 1/2, which is 3 over 1/2, which is 6. And here is the picture of this pretty expanded Y scale, pretty condensed X scale here. When n equals 0, you have 3 over, what's 2 to the 0th power? 1, so there you are at 3. And then when you do add to that 3 added to that 3/2, which is 1.5, so that'd be 4.5, so 1 is 4.5, and then it keeps on trucking. And now you're getting half to this, half to this, half to this, infinitely small difference there. Approaching 6, never quite getting there, but getting very, very close to 6. And that's how your geometric series go. Any questions? Okay. Now, how about this one? What's your A? No. 3 is part of the ratio here. So your A is just 1. A is equal to 1, and your ratio is 3/2. What's happening here?
It's diverging.
Diverging big time. Because your ratio is greater than 1. The absolute value of the ratio is greater than 1. Okay? And as you just look at that, you see everything you're adding is bigger than what you had before. 1 plus 1.5 plus 1 and 5, 1 and 2 1/4 plus 3 and 3. They keep getting bigger and bigger. No way that's not going to diverge. Big time. Okay? Because the ratio is greater than 1, not just greater than or equal to, greater than 1, that series diverges. Okay. Now, they're skipping example 4, so let's go back and do example 4. Okay? Erase my scratch here and do example 4. Now, example 4 is one of those that you can go to LarsonCalculus.com for an interactive version of this type of an example. Use a geometric series to write, here we go, 0.08, and that's what's being repeated, so they put a bar over that, as a ratio of 2 integers. Okay, now what they're going to do is going to be perfectly fine, but it's so much easier to do it the way I was just describing before, basically how we proved the geometric series. Okay? And I'll let you follow what's in the book. I'll show you basically the easy way to do it. The number we're looking for, the fraction we're looking for, I want to give it a name. Let's call it capital L for fraction. Okay, that's not a very creative name. It's 0.0808080808 ... You get the general idea, right? Now let's multiply by the number that moves that decimal the repeating unit 2 away, so that'll be 100 times F will be 8.0808080808 dot dot dot, and it just keeps on going, right? Well, let's subtract, okay? And we'll do 100F minus F is 99F, where F is the number we're looking for, the fraction that we're looking for, is equal to 8, because these all disappear. And then divide both sides by 99. There's the fraction. The ratio of two integers, F is equal to 8 over 99. Okay. Now, they got the same thing. They did it by using the geometric sequence. And what you had to notice here is that the common ratio between all of those is this is why it takes a lot more insight than what we did. Okay, so what we have here, the 0.080808 dot 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 is the same as 8 over 100 plus 8 over 10,000. Whoops, 10 didn't show up. Plus 8 over 100,000 plus, you know, if you just look at this, that's 8 over 100. That would be, add to that 8 over, oh, I'm sorry, I did do too many, 1,000. I had it right the first time. Okay, 8 over 1,000. No, I was right. 1, 2, 3, 4. No, I had it right. 10,000. Yeah, four places. And then the next. So each of those, that would be 8. And your ratio is 1 over 100, or 10 to the second. Okay? Said this poorly. 8 is the A, and 1 over 100 is the R. And you just keep adding those things up. And here's Ricky. See, that's why the way I did it is so much easier, I think, to see and to grasp. And so, with that in mind, now let's see. They actually have A is 8 over 100, and then the ratio is 1 over 100. I had the ratio 1 over 100, and the number was 8. That would put the 8 in front of the decimal. That would be the next one there. So it's 8 over 100. So the way I did it was so much easier, and this is the ratio is this. So this is your A, and this is your R. And then you do the same thing. Your actual number is A, which is 0.08 divided by 1 minus 100, which would be 1 minus 100th, which would be 99. Yeah, 1 minus 100th is 99. I still don't think that's right. This should not be, it should just be your 8. So it'd be 8 over 99, which is what you get. Seems like theirs doesn't make sense that way. No, yeah, I'm sorry. This would be 0.99. So 0.08 over 0.99, which would be 8 over 99. Theirs is right. Okay. That's a harder way to do it than to do it the way I said to do it, which is basically using the same principle that we use to prove it. You just do it, and it knocks it right out. Okay, now there's one other little remark here. And I think that's worthy of note, but I don't think they hit it in the slide set. Let me just see if they do. I don't think they do. No, they don't. I don't think so. Okay. And let me make that note here. Okay. The convergence of a series is not affected by the removal of a finite number of terms from the beginning of the series. So what they're saying is, what if you have the summation from n equal 4 to infinity of 1 over 2 to the n, and the summation from n equals 0 to infinity of 1 over 2 to the nth. Okay? Well, we know the second one here. The a is 1 and the r is 1/2, and we already have done that. That would be 1 over 1/2, 1 minus 1/2, and that would be 2. Okay? Now, the first series then would be, this one right here, would be the summation of n equals 0 to infinity of 1/2 to the n minus the summation from n equals 0 to 4 of 1/2 to the n. Okay? So we know this one is 2 minus, and this one we can just add up. That would be 1/2. See, no. If you're starting at 0, you start with 1. 1/2 to the 0 is 1. Be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. I think I got them all. 1, 2, 3, 4, 5. Yeah. And what do those add to? Well, we did that earlier. Well, almost this. This would be 3/4, 7/8, 15/16. So 1 and 15/16. So that would be 2 minus 1 and 15/16. So that would be 1/16. Okay. Nope. Oh, okay. We started, I went 1 too many. 1 and 7/8. Sorry. You don't use the fourth one because the fourth one, it actually starts with that. Yeah. You start with n equal 4, so you only go n equal 3. So that would be 7/8. So that would be 1/8. All right. That was just a little thing they did over on the side, because you're subtracting the first 3 terms, because you're starting with the 4th term. Well, it's subtract the first 4 terms because the 0 term is in here, but you leave the 1/16 in there. Subtract off the 1/8. All right. Now, that was just a little aside they did. Now here's the properties of geometric series. I think you'll see these are fairly consistent with a lot of the properties you look at, properties of infinite series, that the summation of, now remember if they don't put limits, you assume it's n equals 0 to infinity. No, n equals 1 to infinity. Okay. I can't remember what they usually start. So if you don't see them, it's n equals 1 to infinity. So the summation of a sub n and the summation of b sub n, both of them they're telling you are convergent series. Now let the capital A, capital B, and little c are some real numbers. Now, not just any old real numbers, it's capital A is a summation of this one, because this is a convergent series. This one's converging to capital A. This one's converging to capital B. Then the following series converge to the indicated sum. So if you have some summation of n equal 1 to infinity, which is what these are, of c times a sub n, again, you can pull the c on the outside, then you have the summation of this, which we know to be a. That's what they tell us right here, so it's c times a. Moreover, the summation of the sum of two sequences is the sum of their summations, which is a plus b. Sum of their convergence. Okay? And the difference is the difference between a and b, a minus b. Usually they write this plus or minus, and you don't write the second one here. Both of these work. And again, this is sort of the linear properties of these infinite series. Now these aren't necessarily, they say here geometric series, it's not limited to geometric series. This is properties of infinite series. If they are convergent series, certainly geometric series, or if the ratio is less than 1, after the value of the ratio is less than 1. But don't let this fool you. This is talking properties of infinite series, not just geometric series. Okay? Now, there is what they call the nth term test for divergence, which is sort of an interesting prospect here. If you have a series, summation of n equal 1 to infinity of a sub n, and you know it converges, then you know this absolutely. The limit as n approaches infinity of that nth term has to be going to 0. Okay? If that's going to anything, even 0.0001, okay? If that nth term is any number greater than 0, then this, let's see, I'm saying that, yeah. Well, saying the way they say here, if this converges, then that nth term has to be going to 0. Has to be going to 0. It can't be going to anything greater than 0. The contrapositive of this provides a useful test for divergence. If this is the nth term test for the divergence, it states that if the limit of the nth term of the series does not converge to 0, then the series must diverge. So if the limit as n approaches infinity of a sub n is not 0, okay, no matter how small it is, if it's not 0, then that has to be divergent. Because if that nth term is anything greater than 0, okay, then you're adding something greater than 0 to whatever you had before. So it can't be convergent. You're adding more to it, and more to it, and more to it. So that nth term has to be, the limit of the nth term has to be 0. Now, what this is not saying is that the limit of the nth term is 0, that guarantees convergence. That's not what it's saying. It just says if it converges, that one has to be going to 0, which then means if it's not 0, it is divergent. But this doesn't mean that just because the limit of the nth term is 0, it guarantees convergence. It doesn't quite say that. It says it going in this direction, and then what they call the contrapositive part of this, if that's not 0, there's no way that can converge. It has to be divergent. Okay. But what is not said is just this alone does not prove that it will converge. If it converges, it's got to be that. Okay. So, for the series, the summation of n equals 0 to infinity of 2 to the n. Is there any doubt in your mind that would diverge? Okay. Because 2 to the n as n gets larger and larger, this gets incredibly large. Okay. No way that could ever converge. So that was a pretty simple one. Okay. The nth term is, let's see, where are we now? Example 5, top of page 604. Okay? Definitely the limit is not 0. Okay? So therefore, that one will be diverging like crazy. Okay? So the limit of the nth term is not 0. In fact, it's infinity. Okay? And the series diverges like crazy. Now, how about this one? The series n factorial over 2n factorial plus 1. Okay? Right off the top, that would seem like it's got to have a limit of 0, the nth term. Okay? But it doesn't. Okay? Because you see, this is so much bigger than that, and then you're adding 1 to it, but it's not. Because if you divide everything here by n factorial, this will give you a 1, this will give you a 2, this gives you 1 over n factorial, which is going to be a huge, n factorial is a huge number, so that's going to 0. But then you have a ratio of 1/2. And that's greater than 0, so this one will not, this one diverges also. Okay, just because you're doubling a really big number and adding 1 to it, that still doesn't give you enough to converge. Okay? The limit is not 0, and the series converges. Now, did you see what I was doing there? Whenever you have this kind of form, and this is going to infinity, what you do is pick the major denominator there, and that would be n factorial. I mean, the biggest number here, n factorial. That's the thing going to infinity. Divide by that, okay? And this gives you 1, this gives you 2, because those go out, and this gives you this. So that gives you 1 over 2 plus 1 over n factorial. This is going to 0, so this is going to 1/2. Okay, so that diverges because even though the ratio is small, it's not 0. If it's anything other than 0, it's going to diverge. All right, so how about this one? The series summation of n equal 1 to infinity of 1 over n. That limit is going to 0. As n gets large, it's going to 0. Does that guarantee it converges? No, it says if it converges, the limit has to be 0, but that doesn't, you can draw no conclusion. Here's what they say. Because the limit is 0, the nth term test for divergence does not apply, and you can draw no conclusions about convergence or divergence. Now, later I think we'll find that one, I'm pretty sure it does diverge, but you can't do it with the nth term test. The nth term test says if it converges, the limit has to be 0. If the limit is not 0, then it diverges. But it doesn't say that just because the limit is 0, it guarantees that. Now, as they say here, this series right here will play an important role in this chapter. Fortunately, we're not doing much more in the chapter. So let's do, I don't think they do, example 6. So, whoa, I think that is pretty close to what we were just doing, but let's see. A ball is dropped from a height of 6 feet and begins bouncing, as shown in figure 9.7. The height of each bounce is 3/4 the height of the previous bounce. Find the total vertical distance traveled by the ball. I hate to have to draw this. I wish they'd have shown me this one. Okay, let's try it. Okay. Okay. 1, 2, 3, 4, 5, 6 feet. Okay? And this is the number of bounces. Okay? Okay. All right. Now, the deal here, the ball has no horizontal movement here. We're not worried about horizontal movement, even if it did. We're only interested in the vertical. The only reason they separate the bounces here is so you can see it better. Otherwise, it would be just like this. You know, you wouldn't be able to see anything. So it's dropped from 6 feet and goes down to the first bounce, and it goes back up 3/4 of its first height. Well, 3/4 of 6 is 4, isn't it? Yeah. No, that's not right. Nine halves, which is 4 1/2. They would have to make it something nasty like that, wouldn't they? Okay, then it goes down to the second bounce. So it travels from here to there and there to there, and then it travels each time 3/4 of the way back up to of the previous bounce. Okay, so it keeps bouncing for a while. Okay, I'm not going to draw them all in. You can look at the book or something like the book, or you can draw your own, whatever you want to do. Okay, so the first bounce is 6 feet, and then so it falls 6 feet plus 3/4 of 6 feet plus another 3/4 of 6 feet, right? Because it hits back to the floor again, and then plus 3/4 of 3/4 of 6 feet, right? Okay, plus again 3/4 of 3/4 of 6 feet, because it goes back up again. Okay, so it's 6, 3/4 of 6, another 3/4 of 6, 3/4 of that, plus another 3/4 of that, plus 3/4 of that. You know, so it just keeps going up and down like that. So what we have here is 6 plus 2 times 3/4 of 6 plus 2 times 3/4 of 3/4 of 6 plus 2 times 3/4 of 3/4 of 3/4 of 6. You get the general idea, right? So what's our deal here? The 6 is common to every term, but 2 times 3/4 of 6 is common to every term after that. So let's take this one out, plus, and that would be 6/4 would be 3/2 of 6 plus 3/2 of 3/4 of 6. Yeah. And so our common factor here is 9. So it's 6 plus 9 times 1 plus 9 times 3/4 plus 9 times 3/4 squared plus 9 times 3/4 cubed, and so on like that. I believe that's right now. Okay? So after this, the 15, the first two here, then after that you've got a common factor, your A of 9 and your R of 3/4. Right? Well, this summation from here on out is going to be 9 over 1/4, which is 36 plus, what did I say, 15? Yeah. And that should be 51. So I think it's 42 feet. I took out too much. It's just 6. They count the first one. Okay. So I took out that. So it's 9 plus 36, which is 45? No, 42. I can't even add. No, I took out the 9. I should have left the 6 in there. Plus 6. And that is 42. Okay, sorry about that. You keep that first term. This term. Okay. I took out too many. Still should have worked. No, it shouldn't have. That would have been a smaller number here. Okay. But you get the general idea of it. They didn't show it on the slide, but so yeah. Okay. All right, that finishes 9.2, and that's all we're going to do in the chapter. Homework exercises here would be any of the odds 5 through 9. They should all be at Calc Chat. Any of the odds 11 through 17, they should all be at Calc Chat with 11 at Calc View. Any of the odds 19 through 23, they should all be at Calc Chat. 19's at Calc View. 25 or 27 or both, they're at Calc Chat. They're not at Calc View. 29 to 37, they're all at Calc Chat. 33's at Calc View. 39 to 43, they're all at Calc Chat. 39's at Calc View. 45 through 57, they're all at Calc Chat. 47's at Calc View. 51 should be at Calc Chat. You can explore using that. You don't have to if you don't want to. Any of the odds 61 to 65, they should all be at Calc Chat. 67 should be at Calc Chat. 69 should be at Calc Chat. Any of the odds 71 to 81 should be at Calc Chat. Some of those are pretty interesting. I mean, they're all, I'm sure, pretty interesting, but number 73, multiplier effect, that's a fairly interesting concept there, so might really, let me back up. Let's make it 69 to 75, any of those. Then do 77, that's a probability one. And then any of the odds 79 through 79 or 81. I'll let you decide that. And then they all are at Calc Chat. 83 or 85, they should both be at Calc Chat. 87 to 89 or 89, they should be at Calc Chat. 91 through 95 are true false, so they should be at Calc Chat. 97 through 101. I'll let you choose any of those you may choose. Okay. All right. There's a section project that looks sort of interesting. It's called Cantor's Disappearing Table. You might get a charge out of looking at that, or not, depends on what charges you. Now, I'm not going to hold you responsible for 9.3, but I think that is important enough that I ought to at least expose you to it. So what we're going to do now, I think we've finished the section here, is discard this, and I think we've gone past our midpoint, right? Y'all want to take a break? I know my stomach's growling like crazy, so I need to go get something to quieten it down. But let's end that. And what I'm going to do is just a slideshow of 9.3. So you're not going to be responsible for it on the test, but just I'm going to hit the high points of it. So if you do need it in the future, you'll know where to go back and check. Okay? And once it comes up, we'll... All right, and we'll go from current slide. Now, what we're going to do here, again, is a quick run through of some of the other content of infinite series. We just don't have time to go into great detail, but here are a few tests that you can do with series. We'll use the integral test. We're not going to use it, but I'll introduce you to it, to determine whether an infinite series converges or diverges. And we'll use properties of the p-series and harmonic series. So we've had geometric series, now we have two more, p-series and harmonic series. But let's start with this integral test, and here it is basically. If f is a positive, meaning it's always going to be above the x-axis, continuous, needs to be that, and decreasing for x greater than or equal to 1, okay, and a sub n, the first of the a sub n, is equal to f of n. Okay, now, if you remember back when we were doing the sequences, we said that you could express sequences as a function. It's just that the function is only defined at integral values. Okay, and that's how we define the sequence. Well, so we're going to use that same principle here. A sub n is equal to f of n. Then the summation of the n equal 1 to infinity of a sub n and this integral from 1 to infinity. And again, remember I said summations and integrals are the same, of f of x dx, either both converge or both diverge. So if you can't tell what's going on here, the nth term test doesn't work. It gives you a 0, so you can't say, you know that it, let's see how to say this, it may converge, but it may not. But that doesn't tell you enough. Then, if that a sub n can be written as a function of n, then do the integral of the function. And if you can tell that that converges, then this will converge. Or if you know that's going to be diverging, then that will be diverging as well. So basically, we use this property here and the integral, and sometimes that's easier to tell than this. Okay? But either they both converge or diverge. Okay? If you were doing this, this would be the integral from 1 to infinity of, if you're doing x's or n, whatever you want to name the thing, 1 over n over n squared plus 1 dn, or probably you'd use x over x squared plus 1 dx and see what's happening with that. Okay? And yeah, so they use the f of x. That is positive, continuous for n greater than 1, greater than or equal to 1. In fact, I would have to say greater than 1. No, greater than or equal 1. That would be fine too. Okay. If that was a minus 1, we wouldn't even bother with that. To determine whether f is decreasing, find the derivative. So remember, that was the other part of that. I'm taking more time than I meant to. Remember, it has to also be decreasing for x greater than or equal to 1. So what we're going to do here is then take the derivative of this function right here, and good old quotient rule, low d high minus high d low over low low. And sure enough, this will be an x squared here minus an x squared there. So you just have 1 over this, and that's definitely, for x is greater than 1, that's decreasing, and decreasing pretty dramatically. Let's see, wait, no, I'm sorry. This is x squared minus 2x squared. So it would be 1 minus x squared over x squared plus 1 squared. Okay? And so it's 1 minus x squared over x squared plus x squared. Okay? And let's see, that first derivative is negative for anything n greater than 1. It's 0, let's see, is it? Yeah, 0 at x n equal 1, but it's negative for anything greater than 1. Because with n is x equal 1, this will be 1 plus 1, minus 1 plus 1 is 0, and anything beyond that, this is going to be negative. Because greater than 1, this will be a bigger number than that. This is always positive, so that'll be decreasing from 1 on. Okay? So the f prime is less than 0 for x greater than 1. It follows that f satisfies the condition for the integral test. So if it does, then you can do your integral. Okay? Now, how would you integrate that? You tell me. What would you use? Yes, why not? Let's do a substitution. Let u equal x squared plus 1. du would be 2x dx. There you have to put a 1/2 out in front. And that's what we've done here. And then this would be du over u, which is log. Okay? And why don't they go on and do the integral? I'm not sure. Okay, there they do. The limit as b approaches infinity, because you can't really integrate to infinity, but the limit as b approaches infinity of a log x. Anyone want to make a guess of what that's happening? Logs keep on rising. They don't ever flatten out or come down or anything else. They're constantly increasing. So this looks like to me this is going to be going to infinity. So the series diverges because the integral diverges. So that's how you use the integral test. Okay? Now, p series and harmonic series. Okay? This is always looking a little bit like the geometric test. It has some things in common, but here your p is your exponent, not the ratio, okay? So here is a series of the form of 1 over n to the p. So p is the exponent, not a ratio of your terms. That's called a p series. Where p is a positive constant, always positive, maybe that's why it's p. For p equal 1, this series is called the harmonic series, so this is why we get harmonic series. This is the harmonic series, and that, by the way, the general harmonic series of the form that, okay, and that's a little different from what we just saw, In music, the strings of the same material, diameter, and tension whose lengths form the harmonic series produces harmonic tones. That's why they call it that. So the convergence of this series, this P series is, this converges anytime P is greater than 1, and it diverges for any time P is between 0 and 1. Now, P can't be 0, okay? That would just be 1 plus 1 plus 1 plus 1 plus 1, so that we don't even count that. So P is greater than 0 and less than or equal to 1, even equal to 1. That was our first harmonic series we saw just a minute ago. That always diverges. Only converges if P is greater than 1. Now that P is the exponent in the denominator. So 1.00001, if that's your P here, it will converge. It'll be a big number, but it will converge, okay? Diverge if it's 1 or anything less than 1. Of course, it has to stay positive. So that's your P series. Those are your exponents, positive exponents, in a denominator, okay? Now, so go back to this one here. The P is equal to 1. This one here, remember if P is 1, it diverges. So your harmonic series here, that diverges. And they said earlier, remember this is 1. Important in the rest of the chapter, here it is. That diverges. P is greater than 1, less than 1, greater than 1, it will converge. Anything greater than 1 will converge. Less than or equal to 1, anywhere between 0 and 1, including 1, it will not. Okay. So it says, discuss the convergence and divergence of the harmonic series. Diverges, we just said that. P series with P equal to, converges. We didn't say what it converged to, but all it says is discuss the convergence or divergence. Okay? So here is your harmonic series. 1 plus 1/2 plus 1/3 plus 1/4. So P is equal to 1, got to diverge. If P is equal to 1 or greater, it's going to diverge. 1 or less, it's going to diverge. Okay? If P is 2 or anything greater than 1, 1.00001, it will converge. So that one will converge. That's it for 9.3, integral test and the p-test. I don't know how much further to go. 9.4 is comparison of series. It's kind of like your sandwich theory type thing. It's a really short section, so let's do it real quickly too, so at least you will have been exposed to it. You may not get confected with it, but you'll be exposed to it. Okay? But these will not be on your test, but if you ever need them anywhere in the future, I want you at least to have seen them before. Okay? The direct comparison test for the convergent, let's see, did I skip some things here? Yeah, okay. Yeah. Comparison of series. Use direct comparison test to determine whether a series converges or diverges. Use the limit comparison test to determine whether it converges or diverges. So we have two things sound fairly similar, slightly different though. Direct comparison test for the convergent tests developed so far, the terms of the series have to be fairly simple. The series must have special characteristics in order for the convergent test to be applied. Slight deviation from these special characteristics can make the test inapplicable. Okay? For example, the pairs listed below the second series cannot be tested by the same convergent test as the first, even though it's very similar. Okay? This is a geometric series. That is not. Okay? So you can't use anything like the geometric thing to do that. Because you see, this is part of your counter. If that was not a counter, you can pull it on the outside, but it is a counter, so you can't. This is a P-series test, okay? Your exponent is the thing that's up here. That's greater than 1, that converges. This one, however, n cubed plus 1, though it's so similar to that, you can't use this test to show that, okay? This is easily integrated. Good old goodness, now I can't think of the name of it. Substitution, in substitution, U substitution. You can integrate that pretty easily. However, not that one, okay? I'm not even sure a trig substitution will work for that one, okay? That is a pain in the neck. So that cannot be done that way. Okay. So a direct comparison test, and this is sort of like your sandwich theorem, let 0 be less than or equal to a sub n, and that's less than a sub n, and a sub n is less than or equal to b sub n for all n. So if b converges, the bigger one converges, then a's got to converge because it's less than that. If a diverges, then b has to diverge because it's greater than the a, greater than or equal to. So obviously, if your nth term is bigger, it's diverging. If this one converges, then a smaller term will converge as well. Okay? So that's your direct comparison test. So even though you can't use the same test, you look at these and you know that one does what? Converge or diverge? That converges because your P is greater than 1, okay? Turn that around here. No, okay, sorry. P is up here. This is your geometric test. That would be a geometric sequence, and that would converge. We know what it converges to. But adding something to this makes this actually smaller than that, so therefore that's got to converge as well. Okay? Resembles that term by term. Comparison shows adding something to the denominator makes it a smaller number. So if it's a smaller number, and it does, it has to converge. Okay? And here's the illustration of that. Okay? If this is converging, we knew it did, and this also has to be converging. Okay. The limit comparison test, sometimes a series closely resembles a P-series or geometric series, yet you cannot establish a term-by-term comparison that we just were looking at. Under these circumstances, you may be able to compare second comparison test, which is a limit comparison test, if you can do the limits, okay? So if A sub n is positive, B sub n is positive, and the limit as n approaches infinity of the ratio of those exists. Now this L means it has a limit, where L is finite and positive, okay? Then, if the ratio of those exists and it's finite and positive, then either these both converge or they both diverge. If you know something enough about one to know that it diverges, and that's true, the other one's going to diverge. Or if you know enough to know that one of them converges, and this is true, then they both converge. So that's the limit test. This one, okay? That looks like a harmonic series. In fact, that's what we call the general harmonic series. Yeah, general harmonic series. That's enough like the 1 over n, which you know diverges. So you can do the limit, the ratio of the limits here. the limit of this one over the limit of that one. Okay, now this takes a little bit of manipulation. Multiply both sides, both numerator and denominator, by the product of these two denominators. Okay, we multiply this with that by the product of these two. You'll get, this will wipe out that part. You'll have an n up here, and you'll have this in the denominator. Okay, well, what's the ratio here? This is going to infinity, divided by n, divided by n, divided by n. This will be 1 over a. Okay? 1 over a is finite. All these terms are finite. Okay? 1 over a is finite. And it doesn't matter what this one does. Then that limit exists and is finite. You know this one diverges. Then this one has to diverge as well. The limit test. And because that limit is greater than 0, you conclude that the given series diverges because the one you compare to diverged. Okay. That limit comparison test works well for comparing messy algebraic series, as if they weren't, okay, with a p-series. Choosing an appropriate p-series, you must choose one with the nth term of the same magnitude as the nth term of the geometric series. Okay? So in other words, this one you need the 1 over n squared. Okay? The maximum. This you need square root of n. Okay? This one basically n cubed, 1 over n cubed. And this one, that one converges the ratio, the limits. This will be a 1/3, that will be a 1. You know, everything works out fine. This one's going to diverge. You know this one diverges because your key is 1/2, so that's not going to work. So this one's not going to work. This one will converge. So that one, because the ratio here is in the order of 1 over n to the 3rd. Okay. In choosing a series for comparison, disregard all but the highest powers of n in both numerator and denominator and compare those ratios. All right, so that was that one. This is the way to do these, isn't it? Okay. Goodness. Alternating series. I have a feeling this will go fairly quickly too, not as quickly as those two did, but let's try it. Yeah, I think we'll need this for some of the stuff we'll be doing. I'll show you later, you need to have known this. Well, it may take a while to open. Is this that big a file? I don't know. I didn't see it. Okay. Okay. Again, infinite series, alternating series. Use the alternating series test to determine whether an infinite series converges. Alternate series remainder to approximate the sum of alternating series. Classify convergent series as absolutely or conditionally convergent. Rearrange an infinite series to obtain a different sum. That sounds like fun. Okay, the simplest series that contains both positive and negative terms is the alternating series. These terms alternate sign plus and minus. For example, here's a geometric series. The summation n equals 0 to infinity of -1/2 to the n. When n is equal to 0, that's going to be 1. When n is equal to 1, it'll be -1/2. When n is equal to 2, that'll be +1/4, -1/8, +1/16, -1/32, and on and on and on. Alternating geometric series with r equal -1/2. Alternating series occur in two ways. Either the odd terms are negative or the even terms are negative. Alternating has got to be one or the other. Okay? Now, here's the alternating series test. If a sub n is greater than 0, Okay? The alternating series test, now this is then it's going to infinity. A sub n is greater than 0. They converge when these two conditions are met. The limit of a sub n has to be 0. Yeah, we knew that from before, didn't we? But a sub n plus 1 has to be less than or equal to a sub n for all n. Okay? So this is what we do. This makes the odd terms negative. This makes the even terms negative. Yeah. Is that right? Yeah. Okay. So really doesn't matter there. This, remember, wasn't conclusive before. It was equal to 0. But that's true when everything's positive in an alternating series, as long as the n plus first term is always less than or equal to the nth term, and the limit is 0, then that's going to converge. And basically the reason is, even though that one, the nth term being 0 doesn't convert guaranteed for a positive sequence of series, that could just keep growing slowly. But if it's alternating and they're getting less, then it's zooming in on the equilibrium position. It's got to be. If each term is less than the previous one, or even equal to the previous one, it's going to close in on it. So that's why that will work. Okay. Now, so this one, that right there, diverged, remember? Harmonic series, okay? But if you alternate the signs, the limit of this is going to 0, and the nth term is always less than the n minus first term. In other words, n minus, no, I said it right. The nth term is always greater than the n minus. The nth term is always less than the n plus first term, or the n plus first term is always less than the nth term. One of those two, either one, it means the same thing, then that will converge. So without the alternating, that diverge. With alternating, it converge. Okay? The limit there is 0. First condition is satisfied, but the second one is also satisfied because the n plus first term, 1 over n plus 1, is always less than or equal to. In fact, it's never equal to, always less than 1 over n. Okay? Which is the a plus n term. So therefore, even though 1 over n diverged when you didn't have the alternating sounds, with the alternating sound, it converges. Okay, alternating series remainder. For a converging alternating series, so it has to be converging alternating series, the partial sum of S sub n can be a useful approximation for the sum S of the series. The error involved with using S approximately equal to S sub n is the remainder, is the difference between S and S sub n. Okay? So the alternating series remainder, if a convergent alternating series satisfies the condition that a sub n plus 1 is less than or equal to a sub n, okay, then the absolute value of the remainder, r sub n, which is the difference of those, involved in approximating the sum S by S by S sub n, approximating the sum S by S sub n is less than or equal to the first neglected term. Okay? So that would be, if you're doing the difference here, the remainder of that is going to be less than that next term, the n plus first term, capital N plus first term. If you've done everything up to the capital N term, then the remainder will be less than that because this thing is always true. So the remainder will be less than the next term. Okay. alternate the sum of the following series by its first 6 terms. I don't think we need to do this unless you're actually going to be doing things like this. Let's just see what they do. Certainly the limit of that is going to 0 for sure, because factorials increase really, really rapidly, and 1 over that would be decreasing really, really rapidly. Okay, so the first 6 terms would be that 1, 1/2, 1/6, 2 times 3 is 6, 4 times 6 is 24, 5 times 24 is 120, 6 times 120 is 720. So that would be those alternate signs. Okay. Yeah, I was going to add those together and figure out that's going to be 91 over 144. Okay? Yeah, one of my favorite things to do, which is about 0.63194. Okay? By the alternating series remainder, you have the difference of that is going to be less than the next term. So the next term would be 7 times this. Okay, and that looks like it's about right. And so the difference there, you're within 0.0002 of what you were there. So the sum that's going to be added to it can't be any greater than 6321, okay, approximately. So you're going to be awfully close with that. 63214. Okay. Now, absolute and conditional convergence. I'm not sure all this is all that important. Let's just hit the theorems here. Absolute convergence. If the series of the absolute value of A sub n converges, then that one's also got to converge. If this has some pluses and minuses in it, this is always plus, and that converges, this one's got to. Because otherwise, this one is converging like this, and this is saying this is going back and forth, that's also got to converge. No way around it. Okay? The series summation of A sub n is absolutely convergent when, so we already said this. It's absolutely convergent if the absolute value converges. Then no matter whether if this has any plus or minuses in it, it's got to converge if the ones with all positive converge. This one is conditionally convergent when A sub n converges, but this one diverges. That almost makes no sense. If this converges, then it seems like this, which is the same thing as that, would be convergent. But they say it's conditionally convergent if the absolute value diverges. So that's rather bizarre, but let's move on. And that. Okay. Okay. We know that one diverges, so why do they say it's conditionally convergent? I don't get it, but anyway. I don't think this is all that important, so okay. This may be important, sorry. I don't know where they get this. We'll learn where they got it, but they're just telling you that's equal to log 2. Rearranging the terms of the sequence to produce a different sum. That hardly makes sense, does it? But let's see what they're saying here. Consider this rearrangement. That's, I don't think anything we need to worry about. So the main thing I wanted to get to, I wanted to make sure I got enough covered so it would make sense, is, goodness gracious, they just keep on happening. All right, ratio and root test. Use a ratio test to determine whether a series converges or diverges. Root test to determine whether it converges or diverges. And review the test for convergence, divergence of infinite series. So this is going to sum up several of these. Ratio tests. It begins with a test for absolute convergence, the ratio test. If summation of A sub n is a series with non-zero terms, okay, the series this converges absolutely when the limit as n approaches infinity of the n plus first term divided by the nth term is less than 1. That will converge absolutely, okay? In other words, this term is always greater than that. No, I'm sorry. This term is always greater than that term. The absolute value is always, okay? Now, remember, they may not be, and if it is absolute, and this is not, and this has plus or minus, then this guarantees that the alternating series will definitely converge. This will converge absolutely. However, this diverges when the ratio of the n plus first term is greater than the nth term. That ratio is greater than 1, and certainly when it's going to infinity. That should have been intuitively obvious there. The ratio test is inconclusive, like several have been, if that ratio is exactly equal to 1. Okay? Can't really say that. You can't say for sure it converges or diverges. Okay? I'll just tell you, most of the time, I think it will diverge. Okay? Now, I'll just let you watch how they do it. I don't know that you'll ever be dealing with series that would be complicated like this. But let's just see. Remember, we do the n plus first term compared to the nth term. Okay, the n plus first term would be 2 to the n plus 1 over n plus 1 factorial. And we're dividing that by 2 to the nth over n factorial. But that's the same as multiplying by that. Okay, and that's what they do next. Now, if you'll notice here, the ratio of this to this is going to be 2 to 1, right? Because this is 2 to the n plus first, this is 2 to the n. The first n of them get wiped out, and you're just left with a factor of 2. So the numerator is 2 here. Down here, the denominator is, if you think about what factorial is, this is n plus 1, because n factorial is n times n minus 1, you count down, and this would be counting down for n plus 1, so this will go into that exactly n plus 1 times, because this is n plus 1 times n factorial. So the n factorials go out. So you have a 2 over n plus 1. As n goes to infinity, n plus 1 way bigger than 2. Okay, so that's going to 0. Okay, 2 over n plus 1, and that's equal to 0. The limit is 0. It's a good deal less than 1, so that will converge absolutely. But it converges. Okay. Now, the root test. The next test of convergence of a series works especially well for series involving nth powers. So if the series summation of a sub n then goes from 0 to infinity, 1 to infinity, whatever, converges absolutely when the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. Okay? Now, remember, roots tend to go up more slowly than the values here, okay? So if that root is less than 1, then it's almost certainly going to converge. Yeah, it does converge absolutely. The series diverges when this nth root is greater than 1, okay? If you think about or, and of course if it's greater than 1, if it's infinity, it's obviously going to diverge. That seems almost silly to put that last one in there. And the root test is inconclusive, of course, when it's equal to 1. We see that in so many of these tests. Okay? The square root of this is e to the n. The square root of this, goodness gracious, that would be n to the n divided by 2. Okay? I believe. Okay? I'm sorry, the nth root should have been the same. So this is e to the 2 divided by n. This is n by n divided by n. This will be e squared, and this will be n. Well, e squared is just a number. N is going to infinity. That's considerably less than 1. Okay? So that will, the limit is 0, so that will converge. Okay? And strategies for testing series. First thing to do is the answer approach 0. If it doesn't, hang it up. It can't converge. It's going to diverge. Okay? So if it does approach 0, you can't sell. Okay? But if it doesn't approach 0, it's definitely going to diverge. Is a series one of the special types? Geometric, P-series, telescoping, or alternating? Okay? If it is those are easier to tell. Okay? Can the integral test, root test, or ratio test be applied? Okay? Can the series be compared favorably to one of these special types? And you'll just have to go back and practice on these. I don't think just looking at this quickly, the ratio test would be 1/3 here. That seems to indicate that has a, definitely the nth term is going to 0. Well, let's see, is it? No, the nth term is going to 1/3, not 0. So that's probably not going to. So you just have to look at those, and we're not doing this, so you're not responsible, but would be good things to look at. It diverges, so I'm just going to scroll through these. You're not responsible for them. So here's a summary. If you ever need it, it's out there. Freeze it, copy it, whatever you need. Here's more. And that's it there. So let's see. The main thing I want to get at, now this is just taking way too long to get there. Okay. Slideshow. Current slide. Finally. Taylor polynomials and approximations. Have y'all ever used the Taylor approximation, Taylor series? Sure you have. Anytime you use your calculator, just about, you're doing a Taylor series. That's how calculators function. Interesting application here. Find polynomial approximations of elementary functions, these are the objectives, and compare them with the elementary functions. We'll find Taylor and Maclaurin. They're very closely related. Maclaurin are more restrictive in a sense than Taylor is. Polynomial approximations to elementary functions will use the remainder of a Taylor polynomial. You need to at least be exposed to Taylor polynomials. Okay, polynomial approximation of elementary functions. To find a polynomial function p that approximates another function f, begin by choosing the number c in the domain of f at which f and p have the same value. So your polynomial at c is going to be the same as the function at c. Obviously, they're not going to be matched entirely, but find at least one point where they do, the graphs do cross. Okay? The approximating polynomial is said to be expanded about c or centered at c. This is all sort of nomenclature now. Geometrically, the requirement that p of c equal f of c means that the graph of p of c passes through the point c f of c. Of course, there are many polynomials whose graphs pass through the point c f of c. You can come up with a bunch of them. Okay? Your task, should you choose to follow, is to find a polynomial whose graph resembles the graph of f near that point. One way to do this is impose the additional requirement that the slope of the polynomial function be the same as the slope of f at that point. Because if this is your f, here's your f, I was trying to find the f. There's your f, and here's your p. Now, it looks like a first-degree polynomial, linear. You certainly, this would have this point in common, but it's going in a totally wrong direction. So that would not be a good choice. Pick one whose slope is that, okay? And that slope is exactly that right there, okay? Now, it's not going to be a good choice very far, but anywhere in this range, here to there, it's going to be a pretty good approximation. It's like our linear approximation we did. You've probably done several times now, okay? With these two requirements, you can obtain a simple linear approximation of f as shown here, okay? That is just a linear. You could do even better if you did a parabola that had that point in common, okay? That would fit even more closely. And we're not going to do this, but it's just having you do it. Your function is e to the x, and let's see, what is it? So, x equals 0. At x equals 0, e to the x is what? 1. And the derivative is 1, okay? Because the derivative of f of e to the x is f e to the x. So at 0, that's 1. So a pretty obvious first-degree polynomial that would be there would be the y-intercept needs to be 1, and the slope needs to be 1. So it'd be 1 plus x would be a good polynomial to start. Because p of x is that, you can condition that to include a0 equal 1 and a1 equal 1, so that's exactly what I said, 1 plus x. So here's your exponential function going like that, and here is the polynomial function 1 plus x, y-intercept of 1, slope of 1. Okay? Now, how good of an approximation is that? Out here, pretty good, to over here, pretty good. Back here, getting worse, up here, getting worse. So you want to stay close to that value. Okay. Now, here's what Taylor, and the funny thing is, let me get in the right section here. Well, I don't see, I thought they'd do a little blurb on Maclaurin as well. I'm trying to recall, but if my memory's right, Maclaurin came a great deal later than Taylor did, which is interesting because Maclaurin is a much more, well, I don't see anything in here about Maclaurin except his name. But anyway, Taylor and Maclaurin polynomials. For expansions about an arbitrary value of C, it is convenient to write the polynomial in the form of this. The polynomial function is a sub n plus a sub 1 times x minus c, okay, plus a sub 2 times x minus c squared plus a sub 3 times x minus 3 cubed, so on up to a sub n times x minus c to the nth power. In that form, repeated differentiation produces, of course, that goes to 0 on the first derivative, and this goes to just a1. This would be 2a2 times x minus c to the first power, 3a3 times x minus 3 to the x minus c to the second power, and so on up till. And here are these strange vertical lines that they show up at various places that has no meaning. It's not part of an absolute value thing. It's n times a to the n times x minus c to the n minus 1. But then do the next derivative of it, and you get 2a2. Okay, this goes away because the derivative of a constant is 0. And this goes to be 2a2. 2 times 3, a3. Okay, 2 times 3a3 times x minus 3 to the first power. And you keep on going until this one, without the line here. N times n minus 1 times a sub n to the x minus 3, n minus 2. And you keep doing these polynomials up until you finally get to the nth derivative of the polynomial, and then you'll just have whatever that last term was, which is n times n minus 1 times n minus 2. Keep going until you get to 2 times 1 times a sub n. And you stopped, okay? You don't have any more x's in there because you've derived them away. You've taken derivatives until they've disappeared, because they go down 1 each time, okay? So there's your polynomials and the derivatives. Now, letting x equal c, okay? Go back to this. Letting x equal c, now it looks like to me that everything would disappear because that would be 0, 0. I mean, so this sounds a little bizarre, but letting x equal c, you obtain that p of c, okay, because here it was called p of x, so p of c would be a sub 0, because that would be all that would be left here, because all those went to 0. P prime would be a1, p double prime 2a2, and so on. So that's how they get these, 2a2, all the way up to the nth derivative of that polynomial function with x equals c would just be n factorial times a sub n. Okay? Now, what happened to all these other terms? Oops, I went the wrong way. This is exactly n factorial. N times n minus 1 times n minus 2 times n minus 3 down to n 2, 1, okay, times a sub n. So that's just n factorial there. Now, all right. And because the values of f and its first n derivatives must agree with the values of p sub n and its first n derivatives at x equals c, it follows that f of c must be that, f prime of c must be that, f double prime of c divided by 2 factorial, which is just 2, you know, we've got 2 times 1. That must be a this. And the nth derivative of f at c divided by n factorial would be a sub n. Okay. With those coefficients in mind, you can obtain the following definition of a Taylor polynomial named after the English mathematician Brooke Taylor, and then the Maclaurin polynomials named after the Scottish mathematician Colin. That doesn't sound too Scottish. Maclaurin, that doesn't sound too Scottish, does it? Okay, here's the dates. Okay, this is to me what's a little bizarre. Taylor, from the book, 1685 to 1731, and Maclaurin, 1689 to 1746. So Taylor preceded Maclaurin by just a little bit. They certainly operated jointly for much of their professional lives, but Taylor was actually came before Maclaurin. But it looks like to me the Maclaurin series is a simpler series than Taylor's, and you would think that would have come first, but that's sort of beside the point. All right. So here's the definition of the nth Taylor polynomial and the nth Maclaurin polynomial. If f has n derivatives at c, then the polynomial p sub n, which is f of c plus f prime of c times x minus c plus f prime double prime of c over 2 factorial f minus c squared plus f triple prime, all the way up to the nth derivative of f at c over n factorial times x minus c to the n, is called the nth Taylor polynomial for f at c. So you've taken some function that all it has to have is derivatives. It doesn't have to be a polynomial. It can be a swirly function, really bizarre function. But the polynomial you get from it is going to come very, very close. Polynomials are so easy to mess with, okay? So that's the nth. Now, if that c is always 0, that's the Maclaurin polynomial, okay? If c is equal to 0, then the Maclaurin polynomial, nth order Maclaurin polynomial, will be f of 0, f prime of 0. Taylor is more general at any value c, but if it's if c is equal to 0, then here you have x squared, x cubed, up to x to the n, because c is 0. So it's just a special case of the Taylor polynomials, where c is equal to 0. Okay. Now here's the Maclaurin series for e to the x, which is a nice function, a wonderful function. Its derivatives are beautiful and all like this. So the Taylor, the Maclaurin polynomial for it is 1 plus x squared over 2 factorial, x squared cubed over 3 factorial, and all like this. Just about the simplest Maclaurin polynomial you can imagine. Okay, it's x to the power over that power factorial. Okay, and that sure doesn't do very much credit to them, but we'll get back to a few things later. The remainder of a Taylor polynomial, now we're going back to Taylor, an approximation technique is of little value without some idea of its accuracy. To measure the accuracy of approximating a function value, f of x, by the Taylor polynomial p sub n of x, you can use the concept of remainder r sub n of x as defined here, that the function is equal to the approximate value plus its remainder. If this is the approximate value, that's approximately the remainder, then that should give you the exact value of the function. Okay? So the r of n is the difference between the actual function value and the Taylor polynomial, or the polynomial function for the Taylor R Maclaurin. So the absolute value r sub n is called the error associated with the approximation. Okay? And you usually do the absolute value of it, so you don't mess with the signs. The next theorem gives a general procedure for estimating the remainder associated with Taylor polynomial, and that important theorem is called Taylor's theorem, and the remainder is given by, the theorem is called the Lagrange form of the remainder. So if you haven't had enough possible paper topics, Taylor, Maclaurin, Lagrange, and then you'll have Taylor polynomials, you'll have Taylor series. I don't remember if they call it a Maclaurin series. I think they do. Lagrange has many other things you could write on. There's tons of potential paper topics here. Get working on your paper, somebody. Okay. Here's Taylor's theorem. If a function f is differentiable through the order n plus 1. Now that's a requirement. Some functions don't go very far, but if it is differentiable through n plus 1, like x to the 1/3 is not going to be differentiable very far, because especially if it's at 0, that it won't go very far at all. But if it is differentiable through order n through n plus 1 on some interval I containing your value c, then for each x in I, for every x in I, there exists some z between x and c, such that, getting a little confusing, f of x is alpha c plus f prime of c times x minus c plus f double prime of c over 2. This is exactly Taylor's polynomial here, okay? Plus f prime, the nth derivative of f at c over n factorial times x minus c to the nth power plus your remainder. That's the difference between that and this, okay? Where this thing is now f sub n plus 1 at z at some value between x and c, z, over n plus 1 factorial, which is what you would expect the next one to be, times x minus c to the n plus 1. So basically, this is where you put in the z, that's some number between x and c, okay? And the rest of them you leave as c's. That one right there you leave as a c. And this gives you exactly the remainder. Now you may not know what that value is, but you can at least come close to approximating it. Now, why they start with this, I don't know. The third Maclaurin polynomial for sine x is p sub 3. This is the third Maclaurin polynomial. Is p sub 3 of x is x minus x cubed over 3 factorial. It says use Taylor's theorem to approximate the sine of 0.1, now that's in radians by the way, by p3 of 0.1 and determine the accuracy of the approximation. Okay? Now, we're not going to do that, but I'll let you see how they do it. But remember, for sine, a very good initial approximation is the identity function. Because sine goes up through here, its first derivative is 1 here, because it's cosine, and cosine at 0 is 1. So that makes a really close approximation. And then because the sine function curves down a little bit, if you subtract from it the cubic function, which would be going up like this, that's going to fit it even better, okay? So that sort of makes sense in a qualitative sense, but let's see how we do on it. Using Taylor's theorem, you should have that sine x, which is your actual function, is equal to the Taylor series, x minus x cubed over 3 factorial, plus that remainder. Okay? That remainder is, this is the Maclaurin series, x minus x cubed over 3 factorial, and that remainder is the fourth derivative of f, okay? Evaluate at some value z between c, which is this, 0.1, and 0, which is because you're doing a Maclaurin polynomial, that's at 0. Something between 0 and 0.1. Z is between 0 and 0.1 over 4 factorial times x to the 4th. Okay? Where z is some value between 0 and 1. Fourth one, sorry. Okay? Now, the fourth derivative of sine, if you think through them, sine alternates between sine and cosine. Also alternates sines, S-I-G-N sines, between the two too. So the fourth derivative there, the sine of 0.0 is approximately 0.1 plus 0.1 cubed over 3 factorial, which is a pretty small number, 0.1 minus 0.000167. Oh, you can do that on your own if you want to. That would be 0.001 divided by 6. And you should get that. And the difference between those two is 0.099833. Okay. Now, because the fourth derivative of sine, okay, you did it. Derivative of sine is cosine, first derivative. Derivative of cosine is minus sine, second derivative. Derivative of minus sine is minus cosine, third derivative. Derivative of minus cosine is sine. So you're right back there, fourth derivative of sine z, follows that the area of your remainder at the 3 steps, port 1, can be R3 at this value would be sine of z divided by x to the 4 factorial, 0.1 to the 4th power, and this can be no greater than 1, so they're going to use 1, so it'll be less than this, 0.0001 over 4 factorial. And if you figure out what that is, that's 0.00025. No, 0. Oh, I'm sorry. 4 factorial is 4 to 3 to 2, which is 24. So that thing divided by 24 is 5 zeros and a 4 there, approximately. Okay? Now, here was your estimation. Your remainder is going to be less than this. It may be considerably less than this, but notice that's 1, 2, 3, 4, 5. Is that digit before you get to any change. That's going to be awfully close, okay, to what the real value is, and you've only done 2 terms in your Maclaurin series, and you've gotten how many digits? That 1, 2, 3, 4, at least 4 digits of accuracy. That implies that that's less than that, so it's somewhere in between this and that. Differ by 0.0004 here. You're somewhere in between. That's pretty close. I'd say close enough for government work. Okay. I'm sorry. Taylor polynomials. Now, why did we do those? Because that's leading to well, yeah. This never ends, does it? How are we doing time-wise? Did we just run out of time? Huh? I'm sorry?
I think we're close.
Yeah, awfully close. Okay, sorry about that. I thought this was going to go faster than this. We'll begin next time with power series, just so you'll be exposed to it. Because we've got power series, then representation of function by power series, which will go really quickly, I hope. And then I want you to see Taylor and Maclaurin series. Because we've done the polynomials, we'll then do the series. And that's where we're going to stop. And that is the end of the chapter 2. But these are so ubiquitous. Everybody, everywhere uses them. Your calculators are using them just about everything you do. If you tell your calculator to give you the value of e squared, it's using a Taylor series to do it. I can almost guarantee you that. And it converges and converges really quickly. Okay? That's the reason I want you to see it, because you've used it ever since you've had a calculator in your hand. Okay? They're just all over the place. I didn't want it to take this long though. But anyway, hopefully we'll get there. I did not want to do that either. All right, good deal. No homework on these sections. We're going to pick up, we're skipping chapter 10. Well, I may do a quick PowerPoint show on 10. I had not planned to do it. Well, wait, no, sorry about that. 10.1 we're skipping. I'll just do a PowerPoint show on 10.1. Sorry, because you will need that later in 11. But we're picking up, and you'll be responsible for 10.2, 10.3, and I believe 10.4. Yeah. So we'll soon be through the power shows, hopefully by the first half of next time. And then we'll get into 10.2, 3, and 4, and after that will be your next test. And then we'll do as much as we can in 11. All right, good deal. Have a good weekend. Working on those papers and tests will make it a good weekend, won't it? All right, good deal. That was exciting, I'm sure. Okay. And I just closed down my thing, which I didn't mean to close. All right, here we go again. All right, take care. $13.8. Whoa.
Good one if you can.
All right, thank you. Sorry, I know that was pretty boring, but I'm trying to build to what might be useful. All right. I've got to run down and make some copies, so I'll be a little bit perhaps late getting back, depending on how stacked up they are in the copy room. But I just didn't get to make them earlier. I've got to find my copies first. It's chapter 13. Oh man, it starts right, but it ends wrong. Okay, let's see. 2, 3. 4, 5, 6, 7, 8. That's just the wrong test. There it is. That was scary. All right, how many do we have in here now? One, two, three, 4, 5, 6, 7, 8, 9. So I've got to run down and make 9 copies of this. Before I do that, let me. Oh,